Hi everyone. In this video I'm going to just do the answers to the electric field practice sheet number 2, which is the challenge problems. So I'll start with number 1, which is what is the electric field at the center of the triangle? We have 3 charges. They're all identical other than sign, Q1, Q2, and Q3. The triangles are, or the charges are in a triangle that is an equilateral triangle with 20 centimeters on each side. And the first task that we have is to try to find the central point amongst the charges. And the way that I went about doing that was I drew a line from each charge bisecting the 60-degree angle of the triangle. So there would be 30, 30. And I did that 3 times. So I did this right here, and then I did this right here, and I'm a little bit off with one of mine. I move it. You can see that central point, and that's the point that we're interested in. And because I've bisected every angle, that's a 30, that's a 30. And then we have 90 degrees right here, and 90 over here, and 90 over there. And the electric field vectors that go in, I'm going to draw them in red. If we take electric field 1, charge 1 is a positive, so looking at the central point here, the electric field lines are drawn away from the positive. I'm going to draw that down, and I'll call that E1. And number 2 is also a positive, so from the central point, the electric field line will go away, and I'll call that E2. And from the third point, Q3, from the third charge, the electric field line will actually go towards it because that is the only negative. So there's E3. Our next task is to figure out what these electric field values are, but before we can do that, we need to know the distance between the charge and the central point where the electric field is being measured. So we need to find this distance right here. Now, in order to do that, I'm going to use a triangle. I'll highlight it in green. I'm going to use this triangle right here, and one side of that is 10 centimeters because it's half of the base of this triangle. And we know we have a 30-degree angle, so if I just go below here, and I do my geometry work in green, this is a 30-degree angle. The adjacent side to this is 10 centimeters, or 0.1 meters. And I want to find this distance right here, which is the hypotenuse. So cosine of that angle, this is a right triangle. You can look up here and see the right angle. Cosine of that equals adjacent side over hypotenuse. The hypotenuse equals the adjacent side over cosine theta. The adjacent side is 0.1 divided by cosine of 30. And that hypotenuse value is 0.11, let me look it up, 547. Now, depending upon your rounding, if you store the value, you're going to get an exact answer. If you round it a little bit, you may be a little bit different than me, but as long as the process is the same, I think that's what's important. So 0.11, and I'll just round here and say 5 meters. And it's important to be in meters. You don't want to be in centimeters. So that's our distance to the electric field values. And that's the distance for each electric field. It's a point that's right in the center there. So each electric field is being measured 0.115 meters from the charge that it's associated with. So to figure out E1, that equals K Q1 over D squared. K is 9 times 10 to the 9th. Q1 is 4 times 10 to the negative 6. And D is that 0.115 squared. So electric field 1 equals, it was, when you do the workout, when you do the calculation, you may need to pause the video. I have the value in front of me. 2.7 times 10 to the 6th newtons per coulomb. Now you could do the workout for E2 and E3, but what you would find is that since the distance value is the same for E2, 0.115, and for E3 the distance is the same, and since the charge magnitudes are the same, the electric field values, the magnitudes, are also going to be the same, 2.7 times 10 to the 6th newtons per coulomb, and 2.7 times 10 to the 6th newtons per coulomb. So if you don't feel comfortable making that connection, you can always do all the work out, but they all have the same magnitude, it's just their direction that's different. So once we get our electric field magnitudes for E1, E2, E3, our next task becomes combining the vectors together. And this is somewhat challenging, but what I suggest is breaking the vectors into components. E1 is a fairly easy vector to work with because it's right on the y-axis. It's E2 and E3 that provide a little bit of difficulty. But I'll just take each one and break it into its components, and I'll start with E2. E2 kind of goes up like this. And what I want to do is I want to find E2x and E2y. And the angle that separates them is this angle in here. And that angle turns out to be 30 degrees. We're just bisecting a 60-degree angle that was in there. So 30 degrees. And you could go through and, this is 30, this angle right here is 30, this is 90, so this is 60. All these interior angles are 60. And then if we cut that in half, it's 30, and that's what gets us to our vector. So that's 30 degrees. So what we can write is, if we wanted to do E2x first, cosine theta equals E2x over E2. E2x equals E2 cosine theta. E2x equals 2.7 times 10 to the 6 times the cosine of 30. E2x equals, let me look it up here, it's, I have, and this is somewhat of a rounded value, but I have 2.33 times 10 to the 6th newtons per coulomb. We'll repeat the procedure for E2y. Sine theta, so now we're dealing with the opposite side to this angle. Sine theta equals E2y over E2. E2y equals E2 sine theta. E2y equals 2.7 times 10 to the 6th. The sine of 30, and E2y equals, let me look it up, it's about 1.35 times 10 to the 6th newtons per coulomb. So we can do the same thing for E3, and here's E3 comes down like this, and then there's E3x and E3y. And E3 is just based upon the lower angle, which is also 30 degrees, because these two would have to add up to 60 to be that interior angle there. And you could do this workout again. And what you would find is that because it's the exact same hypotenuse and the exact same angle, E2x equals E3x, and E2y equals E3y. They are identical. And that's very important, actually, because if you look at the E2y and E3y, one is going straight up and the other is going straight down. They're identical values, so it's almost like they cancel one another out. They play no they have no influence on our final vector. What does have an influence are three things. We need E2x, E3x, and E1, which is our remaining vector. And we have to combine those, and that's the last thing that I'm going to do right now. And I'll do that in blue. So the three vectors that we had were E2x, E3x, and E1. And when we put those together, that's going to give us our, that was pretty bad in the drawing, so let me try to do a little bit better of a job here. Not great, but it'll work. That's our net electric field. And then we have a right triangle there because we're working with components. So sometimes when you're working with components, the setup takes a little time, but then in the end you're rewarded with only having to work with a right triangle. And so now we're going Pythagorean theorem. E net squared equals E2x plus E3x squared plus E1 squared. Just going to get a little more room on the page. E net equals the square root of E2x plus E3x squared plus E1 squared. Ready for the numbers. E net equals the square root of, let's see, E2x. Gotta just look that up. Scrolling up 1 second. 2.33 times 10 to the 6th plus another 2.33 times 10 to the 6th. Square that. Plus E1 was, I remember that value, 2.7 times 10 to the 6th. And we're going to square that. I like to put parentheses around this. And our final electric field magnitude is 5.4 times 10 to the 6th newtons per coulomb, depending upon rounding, but that is the exact answer. And finally, as you all know, and that I love to do, I love to find the angle, because it's not a vector without the angle. This is the vector magnitude, but we want the entire vector. So this is an angle we have here. The right triangle, we know the opposite side and the adjacent side. So we can use tangent, and theta equals E1 over E2x plus E3x. And if you recognize that E2x and E3x are the same, you can actually do 2 times E2x or 2 times E3x. It's just a little side note, but it could shorten things up a bit. So back to the angle measurement. Theta equals tan inverse of E1 over E2x plus E3x. And then our end step for ESNA, E1 was 2.7 times 10 to the 6th over 2.33 times 10 to the 6th plus 2.33 times 10 to the 6th. And that angle is our and I believe it comes out to be exactly 30 degrees. And that's south of east. And we'll get a nice little box around this. Not that good. There you have it. That's how you do number 1 on electric field practice sheet 2. So I hope it helps.